Welcome to the second video of this mathematics exam series for Victoria, Australia. In this video, we will solve the last 5 questions from a 2019 trial exam 1 paper.
Hello, math champions. I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything. Hello, this is the second part of the 2019 trial exam paper for mathematics in Victoria, Australia. Question 6 is related to a circular function. We observe the question by comparing its required form against the original one. We here make a plan to use various transformation tools such as dilation factors, x and y direction translations, and or reflections to achieve our target. Usually, it has more than one way to achieve the required function through a series of transformation. As for this question, we start translating pi over 10 units in x direction. After the translation, the new function is shown on the right side. The second step is to apply dilation factor n in x direction. The translated function is also displayed on the right side. The next step is to apply dilation factor 4 in y direction, and the result is shown on the right side. Finally, we translate the function 9 units in y direction, and this is the required function we can obtain. Question 7 is to ask drawing a derivative function according to the given function curve as shown in the diagram. First, we notice that at the point of x equal to c, the derivative function is not defined at this point. Secondly, according to the nature of the original curve, we divide the diagram into a number of sections and analyze them separately. From the point x equal to a to the point x equal to b, the original curve moves down from a very high position in a steep manner and then gradually smooths down to 0. If we look at its gradient, we can say the gradient is increased dramatically from a large negative value and then smoothly move up to 0 at the point x equal to b. Between the points of x equal to b and x equal to c, the gradient gradually decreases again and later is stabilized at the negative constant value. Between the points x equal to c and x equal to d, the gradient starts from a constant positive value and then gradually reduces to 0. From the point x equal to d and the point x equal to e, the gradient of the curve gradually decreases to a negative constant value, and from the point x equal to e onwards, the gradient gradually increases to 0. According to the previous analysis, here we sketch the graph of the gradient function together with the original function graph. These two graphs put together can be used to visually compare the gradient function against its original one. In question 8, the function intersects x-axis at a and b, where both a and b are greater or equal to 0 and b is greater than a. Here, fx is also greater or equal to 0 when x is between a and b. Question A is asking to write an integral to represent the area bounded by fx and the x-axis, while question B asks us writing the integral again to represent the area after x being transformed by applying dilation factors on both x and y directions, plus a vertical translation. Here, question C is asking to express such an area using the area before transformation as well as A and B. Now, to express the area of the region, we need to apply the definition of the definite integral, which is displayed here. However, there is an assumption that fx is continuous in the given domain. Following the above question, here we do the transformation in a step-by-step manner. The first two steps shows the transformed function after applying dilation factors of square root 2 in both x and y directions respectively. The third step shows the function after translating square root 2 units in y direction. The last step shows the area of the region represented by A2. It is bounded by the transformed function fx and the x-axis. Due to the dilation factor in x direction, the original x-axis intercepts are changed from A to square root 2a, from b to square root 2b. So the lower bound and upper bound both are changed accordingly. The vertical translation of square root 2 in y direction also increases the bounded area, which is equal to square root 2 times the dilated distance between the two x-axis intercepts. Finally, we find the required area. Question 9. Country town A has a population of 100,000 people, and 10,000 of them are overweight. A sample of 400 people is selected from them randomly. Question 1 is asking to calculate the standard deviation of the sample proportion. Question 2 is asked the probability when the sample proportion is greater than 0.1. Question 3, assuming n is the number of overweight people in a sample of 400 people from country town A, and asks us to find the probability when overweight people between 10 and 70 in the sample. Question 4 tells us a random sample of 400 people is taken from another town. If there are 40 overweight people in the sample, ask us to calculate an approximate 95% confidence interval for the population proportion P of this country town. Now, since the population is large, the sampling distribution of the sample proportion can be determined by assuming the variable x is a binomial random variable with the parameter n and p. According to the given information, the sample proportion is equal to the population proportion, which is 0.1 in this case. Due to the sample size is also quite large, the sample proportion distribution has an approximate normal distribution, and its standard deviation can be calculated using the formula as displayed here. The calculated result is 0.015. For the second question, based on the given sample proportion value, which is 0.1, the standard deviation is 0.015. Therefore, the probability of greater than the sample proportion, obviously, is 0.5. According to the sample number, the probability of overweighted people can be calculated by dividing the sample number of 400. So the problem becomes to find the probability of sample proportion between 0.025 and 0.175. After standardizing these two numbers, we find the standardized probability between -5 and 5, which is approximate to 1. Based on the formula to calculate this 95% confidence interval, The calculated confidence interval is between 0.0706 and 0.1294. The last question of this paper is a probability question with a circular function as its probability density function. Here we simply call the probability density function as PDF. In order to calculate alpha in question A, we need to use the properties of PDF. We recall its property that are displayed here in red. As we remember, a PDF must satisfy these two criteria. First, for any x, the value of fx is always greater or equal to 0. Secondly, the total area enclosed by the PDF and x-axis is equal to 1. So, according to the second property, the integrated expression of fx between the interval of pi over 4 minus alpha and pi over 4 plus alpha is equal to 1. Hence, we solve this equation and calculate the value of alpha, which is pi over 12. To calculate the probability between 5 pi over 24 and 7 pi over 24, we have to use these two numbers as the lower and upper bounds to integrate the fx and then simplify the expression to the form of 2 times cosine 5 pi over 12, which can be calculated using the given semi-angle formula stated in question B earlier. You can try it later yourself. However, here we just use the angle addition formula to calculate this value, because 5 pi over 12 can be separated as pi over 6 plus pi over 4. Hence, we worked out the result of 2 cosine 5 pi over 12, which is square root 6 minus square root 2 over 2, as we show here.
If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.